According to National Electrical Code Section 250.64b3, a grounding electrode conductor, or GEC, may be connected to the grounded service conductor at any accessible point from the service entrance to the service equipment. This includes the service panel itself. This exception is applicable to both service-rated and non-service-rated panels. This means you can connect your number 4 grounding conductor from your non-service rated subpanel to the grounded service conductor within the main service panel. Let's review some of the key National Electrical Code requirements for grounding conductors. Firstly, the grounding electrode conductor must be connected to the grounded service conductor either at the service entrance or at any accessible point between the service entrance and the service equipment. Secondly, the grounding electrode conductor must be sized appropriately, and this sizing is dictated by Table 250.66 in the National Electrical Code. Thirdly, the grounding electrode conductor should be installed within the same raceway or enclosure that houses the service conductors. Fourthly, the grounding electrode conductor must terminate at a listed grounding electrode. In your specific scenario, utilizing a number 4 grounding conductor is often suitable for a single-family dwelling. Additionally, installing the grounding electrode conductor within the same raceway as the service conductors aligns with the code requirements. Therefore, based on the information you provided, your installation adheres to the guidelines set forth by the National Electrical Code. It is very important to consult the specific edition of the National Electrical Code that is enforced in your jurisdiction, as code requirements can change between editions. Grounding electrode conductors play a critical role in electrical safety. They provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This quick clearing of a fault minimizes the risk of electrical shock and reduces the potential for fire. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. Table 250.66 in the National Electrical Code provides the specific sizing requirements. It is important to note that the grounding electrode conductor size is based on the size of the service conductors, not the size of the subpole conductors. The connection point of the grounding electrode conductor is also critical. Connecting it to the service entrance or at any accessible point between the service entrance and the service equipment ensures that the grounding electrode conductor is effectively bonded to the grounded service conductor. This creates a solid grounding path throughout the electrical system. When installing a grounding electrode conductor, it is important to follow all applicable codes and standards. This includes using the correct size conductor, installing it in the same raceway as the service conductors, and terminating it at a listed grounding electrode. A listed grounding electrode is one that has been tested and certified by a recognized testing laboratory to meet specific safety standards. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The National Electrical Code provides detailed requirements for each type of grounding electrode. When connecting the grounding electrode conductor to the grounding electrode, it is important to use a listed connector. A listed connector is one that has been tested and certified by a recognized testing laboratory to ensure that it provides a reliable electrical connection. The connection should be made in a manner that is mechanically strong and electrically sound. In addition to the grounding electrode conductor, there are other important grounding conductors in an electrical system. These include the equipment grounding conductor and the bonding jumper. The equipment grounding conductor provides a path for fault current to return to the source from electrical equipment. It is typically a green or bare copper wire that is run with the circuit conductors. The bonding jumper connects the metal parts of the electrical system together, such as the metal enclosures of electrical equipment, metal raceways, and metal water pipes. This ensures that all metal parts of the electrical system are at the same electrical potential, which reduces the risk of electrical shock. It is important to properly size and install all grounding conductors in an electrical system. This will help to ensure that the electrical system is safe and reliable. Improper grounding can lead to electrical shock, fire, and equipment damage. The National Electrical Code provides detailed requirements for grounding electrical systems. It is important to consult the National Electrical Code and follow all applicable codes and standards when installing or working on electrical systems. Remember to always de-energize electrical circuits before working on them. Use appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Always double-check your work and ensure that all connections are tight and secure. Electrical systems should be inspected regularly to identify and correct any potential problems. Regular maintenance can help to prevent electrical problems and ensure that the electrical system is operating safely and efficiently. The principles of grounding are based on fundamental electrical theory. Grounding ensures that non-current carrying metal parts of an electrical system are at or near ground potential. This minimizes the voltage difference between these metal parts and the earth, thereby reducing the risk of electric shock. When a fault occurs, such as a short circuit, the fault current flows through the grounding system back to the source. This high current flow causes the overcurrent protective device, such as a circuit breaker or fuse, to trip, interrupting the flow of electricity and preventing further damage or injury. The effectiveness of the grounding system depends on the impedance of the grounding path. A low impedance path allows for a large fault current to flow, which quickly trips the overcurrent protective device. A high impedance path limits the fault current, which may not be sufficient to trip the overcurrent protective device, resulting in a prolonged fault condition. Several factors can affect the impedance of the grounding path, including the size and material of the grounding conductors, the length of the grounding conductors, and the quality of the connections. It is important to use the correct size grounding conductors, keep them as short as possible, and make sure all connections are tight and corrosion-free. Grounding is not the same as bonding, although the two are often used together. Grounding connects the electrical system to the earth, while bonding connects the metal parts of the electrical system together. Bonding ensures that all metal parts are at the same electrical potential, which reduces the risk of electric shock. Both grounding and bonding are essential for electrical safety. They work together to provide a safe and reliable electrical system. In addition to the National Electrical Code, there are other standards and regulations that may apply to grounding electrical systems. These include the National Electrical Safety Code, which covers electrical safety in the workplace, and the Occupational Safety and Health Administration, or OSHA, regulations which cover electrical safety in general industry. It is important to be familiar with all applicable codes and standards when working on electrical systems. Continuous learning is essential for anyone working with electrical systems. Keeping up to date with the latest codes, standards, and technologies helps to ensure that electrical work is performed safely and effectively. There are many resources available for learning about electrical systems, including textbooks, online courses, and training programs. Participating in continuing education courses and attending industry conferences can also help to stay informed about the latest developments in the field. Understanding the nuances of grounding electrode conductor installations is key to providing safe and compliant electrical systems. Remember to always consult the latest version of the National Electrical Code and any applicable local codes to ensure that your installations meet the required standards. When dealing with grounding in subpanels, it's important to differentiate between the grounding electrode conductor, the equipment grounding conductor, and the grounded conductor, also known as the neutral. The grounding electrode conductor connects the electrical system to the earth, providing a path for fault current to return to the source. The equipment grounding conductor connects the non-current carrying metal parts of the electrical system to the grounding system, providing a path for fault current to return to the source in the event of a fault. The grounded conductor, or neutral, carries current under normal operating conditions and is connected to the grounding system at the service entrance. In a subpanel, the equipment grounding conductor must be isolated from the neutral conductor. This is because the neutral conductor carries current, and if it is connected to the equipment grounding conductor in a subpanel, it can create a parallel path for current to flow, which can cause nuisance tripping of circuit breakers and other problems. The equipment grounding conductor should be connected to the subpanel enclosure and to the grounding terminals of the branch circuits. The neutral conductor should be connected to the neutral bus in the subpanel and should be isolated from the subpanel enclosure. Proper grounding and bonding in subpanels are essential for electrical safety. They help to prevent electrical shock, fire, and equipment damage. Always follow the National Electrical Code and any applicable local codes when installing or working on electrical systems. Electrical codes are not suggestions. They are legally binding requirements designed to protect people and property from electrical hazards. Failing to comply with electrical codes can result in fines, penalties, and even criminal charges. It is the responsibility of everyone working with electrical systems to be familiar with the applicable codes and to follow them carefully. Electrical safety is everyone's responsibility. By following the codes and standards, and by using safe work practices, we can help to prevent electrical accidents and injuries. It's important to remember that electricity can be dangerous, and it should always be treated with respect. Never take shortcuts or try to save time by ignoring safety precautions. Always double-check your work and make sure that everything is done correctly. When in doubt, consult with a qualified electrician. They can provide guidance and assistance to ensure that your electrical work is done safely and in compliance with the applicable codes. Electricity plays a vital role in our modern society, and it's important to use it safely and responsibly. By understanding the principles of electrical safety and by following the applicable codes and standards, we can help to prevent electrical accidents and injuries and ensure that electricity continues to serve us safely and reliably. Always prioritize safety when working with electrical systems.